Hi, my name is Abhishek Gade, and today we'll be discussing about the void fraction or the vapor volume fraction in a cavitation model. So, in a simulation, especially in a cavitation model, there are possibilities of bubbles inside the liquid. So, how actually this fraction is calculated? That is what we are going to see forward. So it all starts with defining the equation, the first equation, the vapor volume fraction or the void fraction will be equal to the vapor volume divided by this cell volume. Now the vapor volume would be equal to the number of bubbles volume inside the liquid. So there is a cavitation, there is a fluid inside, the color is blue, and you can see that there are some bubbles formed due to cavitation. That vapors, those bubbles, those spherical bubbles are going to take up some volume, and that is called as the vapor volume. So there is a cell volume and there is a vapor volume inside it. Moving next, what can we say for the cell volume? It is the sum of the liquid volume as well as the vapor volume. A cell has both liquid and vapor. So we can write the denominator as V cell would be equal to V liquid plus V vapor. So now the phase fraction becomes the volume of vapor divided by the volume of liquid plus volume of vapor. Oh, I should tell it specifically. The vapor fraction, the void fraction. Okay. Next, so what happens is how to do something, we should do something that this vapor volume comes in terms of the liquid volume. So let's start thinking about it. So what is actually a vapor volume? If we imagine there are bubbles inside, a lot of bubbles, we can assume that all of these bubbles are having a spherical shape. We know that the spherical shape has volume 4 upon 3 pi r cube. Now, if I know the volume of one bubble, consider all the bubbles are of same size. Yeah, we can consider it for simplicity. And if I multiply by the number of bubbles inside it, then I'll get the total vapor volume, right? So I'll substitute this total vapor volume, that is n into number of bubbles into the volume of one bubble, that is 4 upon 3 pi r cube, 4 upon 3 pi r cube in this equation. So the equation changes as seen on the right hand side. So you are substituting in the vapor volume both in the numerator as well as in the denominator. Now we know that we have to do something, that we want to make this substitution in the form of liquid volume. So what to do? So this number of bubbles can be defined as how many bubble concentration is there per unit liquid volume multiplied by the liquid volume. So it can be specified as something of liquid volume, some percentage of liquid volume, right? So you can also call it as the bubble number density, the bubble per meter cube, bubble per meter cube. How many bubbles are there per meter cube? That could be small n. So capital N, that is the number of bubbles, can be equal to the small n into the liquid volume. That is the number of bubbles per unit volume into the total pure liquid volume. So capital N is substituted as small n into VL both in the numerator as well as the denominator. Let's see what happens next. Now something we see, like we can cut out in numerator as well as denominator the liquid volume. So finally we divide both the numerator and denominator by liquid volume. The liquid volume gets removed from the equation, and now the void fraction or the vapor volume fraction only is a function of the bubble number density, the small n, as well as the radius of the bubble. So alpha is equal to small n 4 upon 3 pi r cube, where r is the radius of bubble, divided by 1 plus small n 4 upon 3 pi r cube. So this is a very important equation which comes while you are studying cavitation models. And yeah, that's all about today's lecture. And thank you. Do subscribe my channel and like the video if it's useful, and keep researching. Thank you.